All right, tonight what we're going to be talking about are colligative properties. And what is the colligative property? Well, it's a property of a certain chemical or substance that depends on only number of the solute particles present. Remember, the solute is whatever is dissolved in that main solution or the solvent. So we're talking about the solute. It has nothing to do with the actual solute's identity. So if I'm talking about NaI versus NaCl, does not matter. Okay, this property will be the same. What's really important though is that your solute needs to be non-volatile. What that means is that it never goes into the gaseous state. It does not evaporate. Okay, so non-volatile never produces the gases. Whereas a volatile solvent will reach an equilibrium where some of the liquid will be into a gaseous state and some of the gaseous state that's right above the liquid will go back down into the liquid. Okay, so it reaches an equilibrium with these kind of shift, whereas a solute, a non-volatile substance, will never go into that gaseous state. So it'll always be in that liquid state. Okay, so it's really important that you're also talking about non-volatile solutes, which we will be in this class. We won't be changing it up. All right, what's really important is, once again, identifying how many particles are produced. That's the only thing. It doesn't matter what the substances are. It only matters how many particles, when dissolved, they will produce. So if I had, let's say, a molecular solid, and if you really want to get a good video, remember, go back to that Tyler DeWitt about how things dissolve. So if I had a molecular, what is molecular again? Well, a molecular solid is something that is covalent, meaning that they are sharing those electrons. And how to identify it? They always start with the non-metal. Okay, so when I put a non-molecular or molecular solid into water to, let's say, dissolve, it doesn't actually dissolve, okay? Well, it kind of dissolves, but it doesn't dissociate. So what happens is that when I have a covalent compound and I put it in water, they separate into their individual components, but they don't, or they separate into their individual compounds, but they don't separate into their individual components. So if I then did the exact same thing, but let's say it was ionic, what happens is that they will actually separate into their individual ions. So if I put in, let's say, 2 particles for molecular, I would end up with 2 particles, and that's it. If I put in for ionic, let's say 2 particles worth, or 2 compounds worth, I guess you would say, what happens is that this guy, who started off looking like this, the exact same thing as the molecular, will actually separate into 4 ions or components. So how do you look at this? Anything that's molecular will only produce however many you put in. So if it's C6H6O6, you would only get 1 C6H6O6. If that had been ionic, which it's not, it would be 6 C's, 6 H's, and 6 O's all separated, so 18, but it's not, so it would only produce 1. On the other hand, NaCl would produce 2 because these would separate. Okay, if you said CaCl2, you would produce 3 because you would have the 1 from the Ca and 2 from the Cl would separate into their individual components. All right, the 3 colligative properties that we are going to be talking about is vapor pressure, boiling point, and freezing point. Vapor pressure will always be lower if you add a non-volatile solute. The boiling point of a substance will always be higher if you add a non-volatile solute, and then the freezing point will always be lower. So let's go into this a little bit. Let's talk about vapor pressure. What is vapor pressure? Vapor pressure is the pressure exerted by a vapor or a gas that is in equilibrium with its liquid in a closed system. So if we look at this, your initial state, this is all liquid, okay? You allow it, what happens is it's going to be allowed to reach equilibrium. So if you notice, the liquid is going into the gaseous state. Once it's reached equilibrium, we've got a certain amount of gas, a certain amount of liquid, and what's going to happen is that some of these liquids are going to go into the gaseous state, and then some of the gas is going to condense back into the liquid state. And that's once equilibrium has actually reached. Now, what's an example of a volatile liquid? Well, water is a great example. One that you guys are very familiar with is actually gasoline. So what happens with gasoline is when you are burning gasoline, what you're doing is you're not actually burning the liquid. What you are doing is you're burning all of that vaporous gas. Okay, so you're not ever burning the liquid, you are just burning the gas that's above that liquid. Okay, so because it's volatile and it could go into the gaseous state, it can burn. All right, vapor pressure. The vapor pressure of a solute in a solution containing non-volatile solute is always lower than the vapor pressure of pure solvent at the same temperature. It's key that we're always talking about like the same temperature because temperature will also have an effect on it. Why does that happen? Well, if we look at these pictures, okay, this guy on the left is a normal solution or solvent, okay, where it's actually going back and forth, reaching an equilibrium. So you've got the liquid going to the gas, gas going to liquid. This occurs at regardless of any temperature, will always occur, okay, just to let you know. Now, when you add a non-volatile solute into the solution, what do you notice about it? Well, you should notice that these particles actually take up space, especially really important for vapor pressure at the surface of that liquid. Okay, so if you notice, it takes up that space. So what's going to happen is that these molecules can't go back into solution as easily, and they can't escape as easily because they're blocked, right? So as you add a non-volatile solute, the solute takes up the space at the surface, which reduces the amount of elements or atoms or particles that are allowed to go into the gaseous state and to also condense back into the liquid state, thus lowering the vapor pressure. Okay, so this is what it says. Vapor pressure of the solvent decreases when the solute increases, meaning the amount of solute. The more solute you have, the more vapor pressure, because what you're thinking about is if you're talking about that the particles at the surface, I'm going to even ignore these. What happens is that if you add more solvent or solute, sorry, if you add more solute, let's say this was 1 molar. Well, now you just block that one spot. If you made it 2 molar, meaning your concentration of your solute is increasing, now you're blocking 2 spots. 3 molar, you're blocking 3 spots. So therefore, the amount of gas or the amount of liquid that could go into the gas or the gas that could go down back into the liquid state is blocked more and more. When you're looking at this graph, okay, what you want to do is focus on just one type of temperature, because remember, this is for when it's the same temperature, it's lowered. So if this is the normal, let's say, vapor pressure right here, okay, at a certain temperature, if you add a solute, what these guys are the solute amount. If you add more solute, 1 molar will make it lower. If I add 2 molar, it will make it lower. If I add 3 molar, because now I have more of these ions at the surface of the liquid, it will also go lower. So as you add more and more ions, your vapor pressure will decrease more and more. Let's move on to boiling point. So the boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the pressure above the liquid, which means your atmospheric pressure. What is atmospheric pressure? Atmospheric pressure is all of the pressure caused by the atmosphere. That's what we're typically dealing with when we're talking about boiling water, because we're open to the atmosphere. If you're in a closed system, then it's whatever the gas is right above that liquid, because you're in a closed system, so it's not open or accessible to the atmosphere. But typically what we're talking about with boiling point is it's when the pressure or the vapor pressure of that liquid is equal to the pressure that the atmosphere is pushing down on the liquid. That is when it will boil. Now, evaporation will occur at any temperature. Evaporations, remember, when it's converting from a liquid to the gas at just the surface. That will occur at any temperature, but boiling point has to occur at a certain temperature, and that's throughout the entire liquid. So once again, boiling point is when your vapor pressure is equal to atmospheric pressure, and that's when you can see these bubbles. Evaporation occurs at all times, at all temperatures. Okay, it doesn't occur at the same rate at certain temperatures as at others, but it will occur at all temperatures. Whereas boiling point has to be a specific temperature because it's when it equals your atmospheric pressure. So a normal boiling point of water is at 760 torr, which is also equal to 760 millimeters of mercury, which is also equal to 1 atmosphere. Okay, so what this is this is at sea level. That's what normal atmospheric pressure is at sea level. Okay, so at sea level, if I were to boil water, it would occur, and it was pure water, it would occur at exactly 100 degrees Celsius. Why? Because at 100 degrees Celsius, this is my curve of my water, my pressures equal my atmospheric pressure. So water can boil at different temperatures. So since boiling point is the temperature where the vapor pressure equals the pressure of the above liquid or atmospheric pressure, changing the pressure of that affects your boiling point. So what is the boiling point for pure water if the pressure is at 40 kPa? So we find 40, go over, go down, and you're talking probably about 76 or 77 degrees Celsius. If it was at 80 kPa, which means less than sea level, so you're actually going up a mountain, okay, where your vapor pressure is, or your atmospheric pressure is less than what is at sea level, you would go 80 and down. So water would boil at that temperature at about 95 degrees Celsius. And lastly, if we're at 150, so you are well above atmospheric pressure or sea level, so somehow you have a lot more pressure than even at sea level. You go down, water would not boil until about 110 degrees Celsius. Now what's cool to note is that your atmospheric pressure changes as you go up in elevation. It actually decreases. That's why people try to train on mountains, because the oxygen actually is less. The concentration of oxygen is less on a mountain than it is down at sea level. So you're working harder because you don't get as much oxygen. But what also happens is that your boiling point changes. I know that on Mount Everest, your boiling point is about 80 degrees. So let's find 80, which is about here. So 80 degrees. So to figure out what the pressure is, you're talking the pressure of that guy is about, on Mount Everest, is about 45 kPa, which is a significant difference compared to what we're normally at, which is 101 kPa. So we have 101 kPa of pressure. So when you go up to the peak of Mount Everest, your water can boil at about 80 degrees Celsius, but you're only dealing with a lot less pressure caused by those outside gases. All right, so boiling point elevation. Boiling point elevation is where your boiling point actually elevates higher than what it naturally does. Okay, so why? In solution, vapor pressure is reduced to compared to that of the pure solvent. And we've already talked about the reasons why. Once again, it's covering the surface and it's not allowed to go back and forth as easily. So liquid boils, and by definition, we've also learned that liquid boils when your vapor pressure equals your atmospheric pressure. So if we look at when we add a solute, you have lowered your vapor pressure. So in order for it to actually boil, you must increase your temperature to make your vapor pressure equal your atmospheric pressure. So boiling point elevation, what happens is if you are at, let's say I'm trying to boil water at sea level, okay? So I've got my normal boiling point. Remember, this is the curve of my vapor pressure by adding my solute. Remember, it decreases your vapor pressure. So normally what I'm talking about is when I'm at 1 atmosphere and I don't change my temperature, my vapor pressure is right here. Well, I still need my vapor pressure to equal my atmospheric pressure if I would like it to boil. So what do I need to do is I need to go over on this curve, which means what did I just do? I increased my temperature. So the boiling point of water, pure water, is lower than that boiling point of a solution with something that's dissolved in it. So if I'm comparing salt water boiling point to boiling point of pure water, my salt water, because it is a non-volatile solute, will actually be higher than that of the boiling point of water. So when we add salt to our water before we do our pasta, we're actually getting above that normal 100 degrees Celsius. All right, so adding a solute increases the boiling point of the same atmospheric pressure. The more solute you add, the more the increase of temperature. Why? Once again, let's go through it. So as we add more solute, what you're doing is you're lowering your vapor pressure. In order for anything to boil, you need it to be at atmospheric pressure. So what do you have to do? You have to increase your temperature. So by me adding more and more salt, I am causing my solution to have to increase its temperature more and more. So even if I added, let's say, a 3 molar solution, that would cause me to have to increase my temperature more and more in order to boil. So where is this important? Well, it's very important when you're talking about car radiators. So what they do is that they add this, there's two different ways. First, they keep pressure on. So when you're doing is you're increasing the pressure. So you're going to be raising the boiling point. So normally, so instead of having it, let's say at normal atmospheric pressure, you're keeping it at a higher atmospheric pressure. So instead of boiling at, let's say, normally water would boil at 100 degrees, it's going to have to boil at, let's say, 102 degrees. Then what they do is they add a non-volatile solute. And so what that does is that increases the temperature needed to boil more. So what are you doing by doing that? You're allowing the water in these radiators to not boil over. Okay, so how do they do it? They add pressure to it, they keep it under a higher pressure, and then they add a solute, which will also raise the boiling point. So both of these will help raise the boiling point, which causes the water in your radiator to not overheat and boil over. Freezing point depression is the last colligative property we're going to be talking about, and what we're going to do is we're going to compare these two systems. So system A is the particles in the solute can shift into the liquid phase at the normal freezing point temperature. So what it can do is it can go into the freezing, it can go into the boiling, or it can go into the freezing, so meaning going to the solid, and then it can melt going into the liquid, and it's reached this equilibrium. Whereas system B, the particles in the solid can't shift into the liquid phase at the normal freezing point, and it can't shift out of the freezing point, so it can't reach equilibrium as easily. Why? Because these solute particles are once again blocking. So it's the exact same reasoning as why the vapor pressure decreased, is because these solute particles are blocking the ability of the other solvent particles from going back and forth into the solid and the liquid state. So what happens is your freezing point lowers. So this is called freezing point depression, looking at this same graph. Okay, so if this is the normal freezing point of water at normal atmospheric pressure, what do you notice as you add more? Well, because it's blocking it, you need to go lower in temperature in order for it to reach that atmospheric pressure, same kind of philosophy. So what happens is it actually decreases your temperature. So whereas boiling point increased as you add more solvent, it does the exact opposite. It decreases as you add more, solute. It decreases as you add more solute compared to that of pure water or your solvent. So where is this important? Well, first off, seawater is a mixture of salt and other things in that water. So what you're doing is you're decreasing that temperature of freezing point. So it allows the water to remain a liquid below the freezing point of water. So it actually can stay liquid state, which is really important for plants and animals to not freeze over at a lower temperature. Okay, it helps. Road salting, that's the one you're going to be most familiar. What it does is allows the street ice to melt at a lower temperature. So instead of melting at 0 degrees like it normally does, it will actually start melting at, let's say, -3 degrees. Okay, the maximum depression of the freezing point is -18 degrees. So if the outdoor temperature is lower than that, it's ineffective. So that's why sometimes it's stupid to put down salt, because if it's -20 degrees outside, it's not going to melt it anyways. It's too far past that maximum depression point of -18. And this is not the common one that's used. Okay, that's -18 is really, really hard to reach. You're talking about it's got a lot of ions on it. The ones that we use don't usually do that. But what happens is that what the whole point of this is that at certain temperatures, it's too cold to even be effective. So icing it or putting salt down is not going to help de-ice anything. Okay, antifreeze. Antifreeze is added to the car's cooling system to keep it from freezing and damaging the engine when the temperature falls below freezing. Why? Because your engine is mostly full of water. So if you add this antifreeze in it, it will shift it over so that it can actually be cooler than zero and still remain a liquid. And then the last one is that organisms that live in the extreme colds have developed a high concentration of these various solutes, which allows them to stay non-frozen when they are surrounded by water and their bodies are mostly made out of water, so that they personally don't freeze into a solid. Okay, so they add all these ions so that they can actually remain non-solid and they don't solidify in these freezing temperatures. The one that does this that you guys might know of is rainbow smelt. All right, hopefully you understand the various colligative properties. Once again, a colligative property only depends on how many ions are produced in the solution as opposed to the exact identity of the solute. You also need to know vapor pressure lowering, boiling point elevation, and freezing point depression are the three colligative properties. You need to understand them, why they occur, and how they affect different things. All right, have a great evening.